A total solar eclipse is an astronomical accident with extraordinary scientific manners. The moon briefly covers the sun, the sky darkens, and parts of the solar atmosphere that are normally drowned in glare become visible. The useful interval may last only minutes, and the shadow never waits for late equipment. That makes an eclipse expedition a peculiar kind of experiment. The laboratory is a narrow moving track across Earth. The appointment was set by celestial mechanics centuries ago. Yet clouds transport failures, vibration, heat, and one hurried mistake can erase years of preparation. For this comparison, the field is not simply beautiful eclipse photography. It is a scientific campaign built around one total eclipse, judged by four things: the importance of its question, the difficulty of obtaining decisive evidence, the durability of its result, and the consequences that followed. Totality creates opportunities that ordinary daylight denies. Astronomers can study the corona, the sun's faint outer atmosphere, separate light into a spectrum, meaning its component colors, or photograph stars close to the darkened sun. Each method turns darkness into a measuring instrument. The strongest campaigns also know exactly what would count as failure. A striking image is not enough. The plates, timings, spectral lines, or other observations must distinguish one explanation from another and remain meaningful after the excitement of totality has passed. This is why remote islands, deserts, ships, aircraft, and colonial outposts keep appearing in eclipse history. Scientists carried precision instruments into places chosen by a shadow, then tried to build a stable observatory where geography had offered only temporary access. Four campaigns stand out. One taught a nation to report an eclipse as coordinated data. Another chased the shadow with a supersonic aircraft. A third found evidence for an element before anyone had isolated it on Earth. The last put a foundational physical theory at risk during a few minutes of darkness. In 1715, Edmund Halley published a map showing where totality should cross England. He also asked observers to report what they saw. The achievement was not merely prediction. It turned a population spread across the eclipse path into a loose scientific network. Halley worked when eclipses still carried a long cultural inheritance of fear and portent. By putting a calculated path on paper, he made the event inspectable in advance. People could stand in the right place, compare the prediction with reality, and send observations back. The map was imperfect by modern standards because the moon's motion and Earth's rotation were not yet known with today's precision. Yet the public corrections were part of the point. The eclipse became a test of calculation, and errors became information rather than embarrassment. Its limitation is consequence. The campaign helped normalize predictive, collaborative eclipse observing, but it did not settle a major physical dispute or reveal a new substance. Halley changed the practice around eclipses more than the underlying picture of nature. 2.5 centuries later, Concorde 001 offered a completely different answer to the same brutal time limit, refused to remain on the ground. For the eclipse of June 30th, 1973, scientists arranged to fly the supersonic prototype inside the moon's moving shadow. An aircraft cannot outrun the shadow indefinitely, but Concorde could follow it across Africa at roughly twice the speed of sound. Special observation windows and instruments turned the cabin into an airborne observatory, while pilots held a carefully calculated intercept course. The result was about 74 minutes of totality, roughly 10 times the duration available to an observer fixed at the best point on the ground. For eclipse science, that was not a longer glimpse. It was a different experimental regime. Researchers could collect extended observations of the corona and other solar phenomena instead of racing through a sequence in a few minutes. The campaign remains one of the most elegant examples of engineering being used to alter the conditions of an astronomical event. But duration alone does not decide this field. The flight magnified observing time and proved a remarkable technique, yet its scientific legacy was specialized. It did not produce one result that permanently reordered chemistry, astronomy, or fundamental physics. The eclipse of 1868 over India brought a more consequential instrument, the spectroscope. A spectroscope spreads light into colored bands crossed by lines. Those lines act like fingerprints, revealing which substances emit or absorb particular wavelengths. Jules Janssen observed the sun's prominences during the eclipse, while Norman Lockyer pursued the same problem independently. Their work helped show that prominences could be studied spectroscopically without waiting for totality, lessening eclipse science from its rare appointment. Within the solar spectrum was a strong yellow line that did not fit the known signature of sodium. It became associated with helium, a proposed element first recognized through sunlight. Helium was not isolated on Earth until 1895. That is an astonishing reversal. Chemistry usually identifies matter in a bottle, a mineral, or a gas sample. Here, light from the sun announced a substance before terrestrial laboratories could hold it. The eclipse helped make the heavens a place where chemistry could be done at a distance. This is the strongest rival because its result was clean, durable, and productive. It helped establish astrophysical spectroscopy and yielded a discovery that survived every later test. Its weakness is not evidence but scope. It revealed new matter, while the final campaign placed a broader theory of nature in direct experimental danger. The 1919 Eddington-Dyson eclipse expeditions are the GOAT of scientific eclipse expeditions. Their target was a prediction from Albert Einstein's general theory of relativity. Starlight passing close to the sun should appear displaced because gravity bends the geometry through which light travels. General relativity, published in its mature form in 1915, replaced the idea of gravity as merely a force pulling across space. Mass and energy curve spacetime, the combined framework of space and time, and objects including light follow paths through that curved geometry. The sun offered a measurable test. Near its visible edge, Einstein's theory predicted a deflection of about 1.75 arcseconds. An arcsecond is 1/3600th of a degree. A simpler Newtonian calculation gave roughly half that amount. Frank Watson Dyson, Britain's Astronomer Royal, recognized that the total eclipse of May 29, 1919, was unusually favorable. The darkened sun would appear against the Hyades, a rich cluster of bright stars, providing several reference points whose positions could be compared with photographs taken when the sun was elsewhere. The logic was simple to state and painfully hard to execute. Photograph the star field during totality, later photograph the same stars without the sun, and measure tiny shifts on glass plates. The difference between the competing predictions was far smaller than a human hair seen from several meters away. Two teams went to different sides of the Atlantic. Arthur Eddington and Edwin Cottingham traveled to the island of Príncipe, off West Africa. Andrew Crommelin and Charles Davidson went to Sobral in northern Brazil. Separate sites reduced the chance that one bank of cloud would destroy the experiment. Príncipe nearly failed anyway. Rain and cloud covered much of the sky, and only brief clearings arrived during totality. Eddington obtained a small set of usable images. At Sobral the sky was clearer, but heat affected the focus of the main astrographic telescope. The smaller 4-inch instrument at Sobral produced the most reliable plates. The larger telescope gave star images whose scale had changed, making its measurements unstable. This awkward division later fed claims that inconvenient data had been discarded to favor Einstein. The historical record is less tidy than either the heroic legend or the fraud accusation. The observers openly described the instrument problems, used the data they considered trustworthy, and published measurements that favored the full relativistic deflection over the smaller alternative. When the result was announced in London in November 1919, newspapers transformed Einstein from a respected specialist into an international celebrity. The public story was irresistible. A German-born theorist had proposed a strange universe, and British astronomers had tested it just after a devastating war. That publicity simplified the evidence. The uncertainties were large. The number of good plates was small, and later instruments would measure light, bending far more precisely. The 1919 result was a strong early test, not the last word that popular memory sometimes makes it. Modern historical reanalysis has nevertheless found no persuasive basis for the claim that the teams manipulated the result. Their treatment reflected the known optical failures, and the surviving material supports the published conclusion within the limits of the experiment. Later observations turned gravitational bending into a routine tool. Radio measurements near the sun improved the precision, while gravitational lensing now uses foreground mass to magnify or distort distant objects. The effect tested in eclipse photographs became a way to detect otherwise invisible matter. The helium campaign produced the cleaner discovery. Concorde achieved the more extravagant piece of eclipse engineering. Halley built the more foundational public observing network, but 1919 wins this exact field because it combined a discriminating question: global operational risk, lasting empirical support, and consequences far beyond eclipse astronomy. Its GOAT status matters because it shows what an eclipse can do at science's highest level: not merely reveal the sun, but make the universe choose between rival descriptions of reality.